One type of reaction that we cover in organic chemistry is called catalytic hydrogenation. This reaction simply uses H2 gas and a catalyst called palladium over carbon to reduce a double bond to an alkane. So what these reagents do, adding hydrogen gas and palladium over carbon, just results in an alkene, a pi bond, becoming a single bond. So what we're doing is we're adding 2 hydrogens, 1 to each of the vinyl carbons, so that we go from 1 hydrogen at the vinyl carbon to 2 hydrogens at the vinyl carbon. Oops. And we'll be covering this again in chapter 6, which focuses on reactions. These are reduction reactions. The number of carbon to hydrogen bonds increases in a reduction reaction. And this reaction occurs, we said that at the beginning of the chapter that molecules that are in the same group have the same characteristics will react in the same way with the same reagent. So cyclic alkenes very much react like regular straight chain alkenes, a pi bond in the presence of hydrogen gas and palladium over carbon will become a single bond. So we go from having this pi bond to a single bond by adding 2 hydrogens. We don't have a specific mechanism of electron transfer for this. My organic professor called it the spaceship model. So that the alkene hovers over the palladium carbon catalyst, which attracts the hydrogen gas to the surface. The alkene hovering over the surface picks up 2 hydrogens, beams them up like a spaceship, and we end up with our final product, which has 2 new hydrogen bonds. We can use enthalpy values to determine the relative stabilities of alkenes. And this is where I like to go in and define the different types of alkenes that we are going to see. So let me get out of this so that I can give you a list. So I'll make the list and then I'll come back on the video. Okay, so here's our table of the different types of substituted alkenes. Alkene substitution, what we mean by alkene substitution is the vinyl carbon to carbon bonds. So vinyl carbon being a carbon that is part of the double bond, how many bonds does that carbon have to other carbons? And we're only counting single bonds to carbon. Okay, so first we have monosubstituted. Well, actually, one thing that should be on the chart would be unsubstituted, but there's only one molecule that is unsubstituted, and that's ethene, which has only bonds where the vinyl carbons only have bonds to hydrogens. So we're going to talk about more complicated alkenes than ethene. Okay, so let's first discuss monosubstituted. Monosubstituted means that from either vinyl carbon for the entire alkene, there's a total of 1 vinyl carbon to carbon bond. So for our generic example, we have an alkene showing vinyl carbon with 1 bond to an R group, where R usually indicates a carbon group. For our specific example, I drew 1 propene. So we have 3 carbon molecule, and from vinyl carbon to other carbons, there's only 1 bond. Next, we have geminal disubstituted. This is 2 bonds to carbon, and geminal means that those bonds to carbon occur from the same vinyl carbon. So this is what the geminal disubstituted looks like. We have vinyl carbon, and that one vinyl carbon has two single bonds to carbon. For a specific example, we can show this butene, which has a methyl group at carbon 2. So we would number from 1, 2, 3, 4. So there's a methyl group at carbon 2, and so it's 2-methylbutene for the name. And this is geminal disubstituted because the vinyl carbon, one of the vinyl carbons has 2 bonds to carbon. Next, vicinal disubstituted, and there are, of course, 2 vicinal disubstituteds. Vicinal meaning that each vinyl carbon has 1 bond to carbon. When we combine vicinal with disubstituted. So vicinal carbons are adjacent vinyl carbons, and then the disubstituted, each vinyl carbon has 1 bond to carbon. So cis, so we have 2 bonds to carbon, and we're talking about vicinal cis. So here's our example. We have our pi bond, and from the vinyl carbon at the left, we have an R group, and from the vinyl carbon at the right, we have 1 R group. So example, 2-pentene, we have that the first vinyl carbon has a bond to methyl, and the second vinyl carbon has a bond to ethyl. That is disubstituted, vicinal disubstituted. Then we have vicinal disubstituted trans. Error. Okay, escape. So let's fix this really quickly. Take this group, move it over. Take the hydrogen, move it up. Okay. So vicinal disubstituted trans, each vinyl carbon has 1 bond to carbon, but those bonds are in the trans or E orientation so that they're on opposite sides of the double bond. One vinyl carbon to carbon bond at the left vinyl carbon, 1 vinyl carbon to carbon bond at the right vinyl carbon. And our specific example, trans 2-pentene, just showing that the 2 groups are on opposite sides and that each vinyl carbon has only 1 bond to carbon, single bond to carbon. Then we have tri-substituted when the vinyl carbons have a total of 3 bonds to carbon. So one of the vinyl carbons will have 1 bond to carbon and the other vinyl carbon will have 2 bonds to carbon. It doesn't matter in which order that occurs. It could be the right or left vinyl carbon. And we have our specific example. So each vinyl carbon, the total number of bonds from a vinyl carbon to carbon should be 3, which means there's only 1 hydrogen bonded to a vinyl carbon. And then we have tetrasubstituted. So tetrasubstituted would mean that our pi bond has 4 single bonds to carbon. So there are no hydrogens bonded to a vinyl carbon. So I just drew R1, R2, R3, and R4. And for our specific example, 2,3-dimethylpentene. So 1, 2, 3, 4, 5, methyl group at 2, methyl group at 3, no bonds to hydrogen from a vinyl carbon. So I put these in a very specific order. You notice to the left, I have arrows. We have that the enthalpy is decreasing as we move towards tetrasubstituted. So the more bonds from a vinyl carbon to a carbon, the lower the enthalpy. The heat of hydrogenation is increasing as we move towards fewer bonds from a vinyl carbon to carbon. And here's our examples. from your text. So we have that this tri-substituted has an enthalpy of negative 26.9 and a heat of hydrogenation of positive 26.9. The geminal di-substituted example has an enthalpy of negative 28.5, which is greater than the tri-substituted. Oh, yeah, that might make it harder. Okay, tri-substituted, di-substituted is decreasing. It's getting lower, which means that it's increasing. Right, because 26.9 is greater than negative 28.9, so the arrow is pointing down to show that it's increasing as we become more substituted, because negative 30.30 is less than 26.9. And then the heat of hydrogenation, 26.9 from the tri-substituted to 30.3 for the mono-substituted. That means that the heat of hydrogenation is increasing as we move towards the mono-substitute. So more substituted, as you get more substituted, heat of hydrogenation decreases. And as you move towards more substituted, the enthalpy increases. And what this is actually meaning, we're going to look at energy graph. The tetrasubstituted has a lower energy than the monosubstituted. So having more bonds from a vinyl carbon to a carbon is considered more stable. So we can add that into the chart. More stable as we get more substituted, less stable as we become less substituted. And you will probably be asked to rank these in order of stability, and you might either just be asked to rank them as stable or from least stable to most stable. You might be asked to rank them, you might be given the heat of hydrogenation and asked them to rank them in order from stability based on heat of hydrogenation, or you might be given enthalpy and asked to rank them based on stability, for stability based on the enthalpy. If they ask for stability, what I do is or they might ask for lowest energy, highest energy, rank them from the highest energy to the lowest energy. So the most stable will have the lowest energy. And we can look at our graph. Here is a graph showing reaction energy potential graph for heat of hydrogenation, or for hydrogenation. The most stable is the tri-substituted. So it has the lowest initial energy. Then they show the geminal di-substituted. And then they show the mono-substituted. And the reason that, so they only give you 3 examples, but the exhaustive table shows all of the possibilities: mono-substituted, geminal, vicinal, cis, vicinal, trans, tri-substituted, and tetrasubstituted. And this order will hold true for this graph. If we were to put them all in the graph, they would be in the same order that I have put them on the table, with the mono-substituted at the highest energy and the tetrasubstituted at the lowest energy. Notice that the examples that they give you, if we use H2 and PDC to get to the alkane, then all of the pi bonds disappear from the addition of hydrogen, and the final product, when these pi bonds are gone, the molecules are all equivalent. They're all the same thing. So these 3 things, when reacted with hydrogen gas and palladium over carbon, create the same product, which is shown at the right. And that they result in the same final energy of that product. But then the change in energy, or the enthalpy of the reaction, is different because the change from the starting material, which had different energies, to the final product, the overall change in enthalpy is different depending on the product that you have. the higher energy your starting material, the greater the change in enthalpy that will occur. So it has a larger change in enthalpy, but remember that negative 30.3 is less than negative 26.9 in terms of numerical value.